So in 12.3, we're going to talk about geometric sequences and a little bit about geometric series, and then you'll see those again in Calc 2. So a geometric sequence may be defined recursively as a, and remember recursively just means kind of like backwards, okay, as a sub 1 equals to a and a sub n divided by a sub n, or I guess it doesn't just mean that, it means built from itself, but we'll see what it's talking about. So a sub n over a sub n minus 1 equals r, or as a sub 1 equals a and a sub n equals a sub n minus 1 times r. Basically, a few things to keep in mind. This is your common ratio. So what makes a geometric series or a geometric sequence so nice and easy to work with is that each term changes by multiplying the term that came before it by the same number each time, okay? So it's a very nice sequence to deal with. Arithmetic is very nice, geometric is very nice. So it's a type of sequence we know a lot about, we like to work with them. And this is called the common ratio. This number that you multiply by, whether it's a fraction or a whole number, this number that you or an integer actually, this number that you multiply by is actually easy to identify, and all you have to do is take any term and divide it by the term that came before it, and you'll get a value. And then you do that for any two successive terms. You take a term and the term before it, a term and a term before it, and you will always get the same number. So that's a way that you can identify if something is a geometric. I mean, you should also be able to kind of look at it and just kind of know. Here's what the terms would look like. So you have your first term a sub 1, then you have your next term a sub 1 times r, you have your next term a sub 1 times r squared. Notice that each term is based on the a sub 1, the first term, and that builds the next term, and that builds the next term. So the term builds the next term, okay? That's what we're talking about, okay? When we say this strategy, I guess you could say. So determine if the geometric series or sequence, or determine if it is a geometric sequence. Sorry, you guys, I'm getting a little ahead of myself. Just trying to get this video in the books. So we have 2, 6, 18, and 54. So the thing is I want to know if this is a geometric sequence. So according to this thinking, all I have to do is see if there's a common ratio. So what I'm going to do is I'm going to take a term, and let's do 54, or let's do 6 divided by 2, right? Because that's this term, the n term, a sub n, divided by the n minus 1. That would be this term, the term that came before it. And then we should be able to do 18 divided by the term that came before it, 6. And we should be able to take 54 and divide it by the term that came before, which is 18. And these better all be the same number. Well, this will be 3 over 1. This will be 3 over 1. And this will be 3 over 1. So they equal 3. So this is my R. This is my common ratio. So if it has a common ratio, then it is a geometric. And you could see that how do you go from 2 to 6? You multiply by 3. How do you go from 6 to 18? You multiply by 3. How do you go from 18 to 54? You multiply by 3. That's what it means to have that common ratio. So it's very nice, easy to work with. We really like geometric series sequences in mathematics. Now here's the nth term of a geometric sequence. So, and again, a sub 1 is our first term. And again, you can't let your R be 0. That doesn't make sense to have your common ratio be 0, because then everything would be 0. That doesn't make sense to talk about it like that. So for a geometric sequence whose first term is a sub 1 and whose common ratio is R, the nth term is determined by this formula. So you just need the first term and you need the common ratio, and then you can build any term in that sequence, okay? So what we're gonna do is suppose that I give you, and I say find the fifth term of the geometric sequence, and the nth term. Okay. So what we're going to do is we're going to give you a sub 1 is equal to -2, and I'm going to tell you that r is equal to 4. Okay. So what I want to do is I want to be able to find the fifth term. Okay. So all I need to do is use my formula. My formula says a sub 5 should be a sub 1, which is -2 times r, but we said r was 4, to the n minus 1. But in our case, what's our n? Our n is actually 5, right? Because we said the fifth term. So this would become -2 times 4 to the 4th, which is 4 times 4 is 16, times 4 is 64, times 4 is 256, I think. Sure. So then this will become -512, I believe. Okay. So that would be a sub 5. Now, if they want to find the a sub n, which would be nice, that means we could then find any term. It's just -2, so a sub 1, times 4 to the n minus 1. And that's it. This is our general term, and this is our fifth term. Okay, so that's all there is to it. It's really no big deal. Okay. Now, what if I ask you to find the eighth term? If we have 1, 3, 9, ... Well, what we need to do is we need to see if it's a geometric. So I'm going to do, let's do one more, 27. So what we're going to do is we're going to find 3 divided by 1, that better equal 9 divided by 3, that better equal 27 divided by 9. So this will be 3, this will be 3, and this is 3. So 3 equals r. So we're good. So then what we want to do is we want to find a sub n. I'm just going to find the general term first, which would be 1 times 3 to the n minus 1. So then if I want to find a sub 8, that'll just be 1 times 3 to the 8 minus 1, which would be 3 to the 7th. And you can just leave this. This is a really big number. Let me see if my calculator can even do it. I'm sure it can, actually. It's not that big. Yeah, sorry, it's just 2187. I thought it was going to be worse than that, like 3 to the 70th power or something. So 3 to the 7th equals 2187, 2187. So we get our final answer right there. So again, it's not really that big of a deal, okay? Now, there is 2 formulas to find the sum. This formula of a sum, of finding the sum of a geometric series. Okay. Well, here's the thing. Your book uses this formula. And I'm going to give it to you guys just so you have it, but this is not the one I'm going to focus on. I don't really concern myself very often with geometrics that terminate, that have an endpoint. The ones that I'm much more worried about are the infinite ones. So this is the formula that we're not really going to use in this class, but it's in your book in case you see it. So the one that we're going to use is for infinite geometric series. And in general, I believe if you call it a series, it's supposed to be infinite in the first place. And if it's not infinite, then it's called a partial sum. But that's just a technicality. I guess it depends on who you talk to. So what we're going to do is we're going to need, so we need to determine convergent or divergence. So what it means to be convergent or divergent for a geometric is if the geometric series approaches some value. So you're going to add up all the terms, and if those terms add up to a specific number or they approach a specific number, we're going to say that it converges. Now, if those terms do not add up to a specific number or they add up to infinity, then we're going to say that it's divergent. So think of finite versus infinite. Remember, you're adding up an infinite sum. So basically in your book, I believe they call it this, S sub infinity. Okay, so for a geometric, so for a infinite geometric sum slash series. Okay, so basically I just want to kind of, again, we're not going to go too crazy on this, you guys. You're going to see this a lot more in Calc 1, or I'm sorry, in Calc 2. But this notation that I'm using up here, this notation that we used in the previous sections, so for an infinite geometric sum or series, we say it is convergent if, the absolute value of R is, less than 1, and divergent if the absolute value of R is greater than or equal to 1. So if the common ratio is less than 1, that determines everything. That means it's convergent, a convergent geometric series or sum. So if convergent, the sum can be found using this formula. S infinity equals, and I don't use that in my calculus class, but in your book they call it S sub infinity, equals A sub 1 over 1 minus R. Okay, this is equivalent to saying the sum from n equals 1 to infinity with k equals 1. Your book uses k a lot. K equals 1, A sub 1, R to the k minus 1. So basically, if you have it in the form that they want, like this, you can say that it is if you can show what R is less than 1, then you can say it's going to converge to this sum right here. So this is your sum. So that's a lot of talk. Let me show you what it means. Okay. So suppose I gave you, so I'll say like on the test, determine if the following is convergent or divergent. If convergent, find the sum. So then I'll give you something like this, 2 times 2 over 3 to the k minus 1, okay? So you should instantly know if this is a geometric or not, and this is n equals 1 to infinity, or sorry, k. In my other book, we use n equals 1. This book uses k. So it's just a notation. So instantly, you should know that R is worth, R equals 2/3. And we know that since the absolute value of 2/3 is less than 1, it is convergent, okay, by the geometric. And because it's convergent, we know the sum is equal to A sub 1. So now we have to find A sub 1. Well, A sub 1 is just 2, right? And this is my R. So this is definitely in geometric series form. And the sum will be 2 over 1 minus 2/3. And then that's all we do. So we do 2 divided by 1/3, which would be 6. And we're done. That is the actual sum. And that's all there is to it. Now there's something cool we can do, is I can ask you to show that 0.9 bar equals 1. Okay, now you may not think it does, but what if I told you that you could write out 0.9 bar? So 0.9 bar is this, right? Right, but that's actually 0.9 plus 0.09 plus 0.009 plus 0.0000, so on and so on and so on, right? But I could actually write that as 9/10 plus 9/100 if I wanted, 9/1000 plus 9/10,000, so on and so on and so on. However, I can tell just by looking at this that what do I have to multiply by to get from 9/10 to 9/100? I multiply by 1/10. I multiply by 1/10. I multiply by 1/10. I multiply by 1/10. That means that R is worth 1/10, right? So we know this is a geometric actually. And you kind of already know the idea behind this, because what if I told you 0.3333 plus 0.333333 plus 0.333333, so on and so on. Well, wouldn't you say that was 0.9999999? And again, this isn't a proof. This is just kind of where you can maybe justify that you already knew this. Well, isn't 0.33333 really just 1/3 plus 1/3 plus 1/3, which is 3/3, which is 1? Now, this is not like a proof. This is just thinking about it, like justifying it. This, we're actually going through and we're going to show how much it's worth. Okay, so now I get to say that my a sub 1 is worth 9/10. I get to say that my R is worth 1/10, which is less than 1, which means convergent, geometric, right? It's a convergent geometric, okay? And we can find the sum, the infinite sum. And again, that's the weird part. Remember, we're adding to infinity. So we're adding forever. And we're saying even adding an infinite amount of terms, it will still approach some value. And that value, and let me do it fancy. Let's do the S infinity like your book does. S sub infinity. So this is the infinite sum. We're going to say a sub 1, which is 9/10 divided by 1 minus 1/10, which would be 9/10 divided by 9/10, which is equal to 1, which is what we wanted to show. So this is a way that you can do this problem. For any repeating decimal, you can do this if asked. And you just kind of write it out as decimals that are being added. Then you switch those decimals to fractions because every decimal placeholder is a tenth. You know, a 1/10, you keep multiplying. So you could make it work like that. There's problems, application problems with bouncing balls that we might do in Calc 2, where, you know, you can calculate, you know, the distance traveled by a bouncing ball because it decreases by the same amount each time. Let's say it's like 1/3 of the distance each time it bounces. So that's a geometric series. If you added up all the distance, it's a sequence, but then if you want to know the distance, that would become a series, because a sequence is just a list of terms, a list of numbers, list of values. A series is the addition of those. So the moment I write this notation right here, we are now talking about a series. We are no longer just talking about a sequence. This is the sequence that builds the series, but when you give sigma notation or summation notation, you are now talking about a series that you're adding all the terms up, and that has its own type of pattern and stuff like that. So this is something that you will see again in Calculus 2, but I just wanted to kind of give you guys a little background on it, on sequences and a little bit of geometric sequences and series, but there's more to it that you'll learn in Calculus 2. All right, you guys, thanks for watching. That's this video.